Hello students, in this video we'll see how to solve non-homogeneous first-order systems using Dunhamel's formula. So, to solve the system x prime equals a x of t, this is the ordinary homogeneous equation, plus f of t, a forcing function, which makes it non-homogeneous. We use Dunhamel's formula. And this formula is given as follows. It tells us that x of t is the exponential of at x of 0, our constant initial vector, plus the integral from 0 to t, the exponential of a t minus s, f of s ds. So in order to solve a non-homogeneous system, we need to compute the matrix exponential of the matrix A, right? So let's see an example of this. Let's solve x prime of t is going to be the matrix A, which is negative 2, 1, 0, negative 3, x of t, plus this non-homogeneous part, which is 1, 3. So in order to apply Dunhamel's formula, I need to be able to compute the matrix exponential of this matrix over here. So let's first compute the exponential of the matrix negative 2, 1, 0, negative 3 times t. So to do this, we'll need to find the eigenvalues of this matrix. But since this matrix is upper triangular, its eigenvalues are the entries on the diagonal. So the eigenvalues are negative 2 and negative 3. And we can find the eigenvectors the eigenvector that corresponds to lambda equals negative 2 will come from the matrix 0, 1, 0, and then I'll have a negative 3 minus a minus 2, so that'll be a negative 1. v1, v2 equals 0, 0. We'll get our first eigenvector, v1, v2, will be 1, 0. Similarly, when lambda is equal to negative 3, our matrix will look like this. I'm going to subtract off negative 3 from the diagonal. I'll have a 1 and a 1, and then I'll have a 0 and a 0. And from this, I can see that my eigenvector will be 1 and then negative 1, or I'll put a negative 1 on top. So from this, I can find my matrix P. My matrix P of eigenvectors will be the matrix 1, 0, negative 1, 1. Now I can find the inverse of P by flipping the diagonal entries, negating the off-diagonal entries, and dividing by the determinant of the matrix, but the determinant of the matrix P is equal to 1, so there's no need to divide by anything. From this, we see that A, our matrix A, times T will be P, which is 1, negative 1, 0, 1, times the matrix of diagonal matrix of the eigenvalues, so negative 2t, 0, 0, negative 3t, times the matrix P inverse. The matrix P inverse will be a 1, 1, 0, and a 1. From this, we can now see what the matrix exponential of e to the at is. E to the at will be P, 1, negative 1, 0, 1. Then the exponential of the diagonal entries, e to the negative 2t, 0, 0, e to the negative 3t. And then P inverse, 1, 1, 0, 1. from this, I can now apply Dunhamel's formula. Dunhamel's formula tells me that x of t will be e to the at x of 0. So it will be the matrix 1, negative 1, 0, 1. Then e to negative 2t, 0, 0, e to negative 3t, 1, 1, 0, 1. Then x of 0, y of 0. And then that corresponds to this first term over here. And this first term over here is referred to as the homogeneous term. So this is my homogeneous term. And this term over here is going to be my particular solution. And that's the term we added next. So this term over here is the homogeneous solution. And now I will add in the particular solution. So the particular solution will be the integral from 0 to t. This whole matrix exponential with t replaced with t minus s. So we will have a 1, negative 1, 0, 1. Then I will have an e to the negative 2 t minus s, 0, 0. E to the negative 3 t minus s. And then I'll have the matrix P inverse, which we found to be 1, 1, 0, 1. And then this matrix e to the at minus s is operating on the forcing vector f of s, which in this case is a 1 and a 3. So this will be operating on 1, 3 ds. And this expression over here is my particular solution. So I have a homogeneous solution and a particular solution, and the final step in the problem is to simply perform all of these multiplications and to write it as one vector. Now, if the forcing function had variables in it, say for example the forcing function looks something like t squared, over in this area over here I would replace this 1, 3 with not t's, but rather the variable of integration s, so I have an s and an s squared, for example. So depending on what the force function is, it's important to notice that while there are t's in the forcing function in the original formulation of the problem, when you use the Dunhamel formula, the actual integral term must be converted to the new dummy variable of s. Thank you very much.